finger MTN 555-3760-5465-00614. Who got it? You got it. Oh yeah, stand up. That guy. Let me see. Oh yeah, load it. Load it.
Hey, got the number.
Yeah, he got it. Wait. Call it again. Go and sit down. Go. No, it has gone again. Let me call it for the last time.
No, don't call it again.
Call it another one, Abi.
Give me your this thing.
Just give him your number. Should we do another one? Oh yeah, before then, everybody bring out your phone. Go to YouTube. Before wait now. You will subscribe, oh. Now give away they give like this. If you have not subscribed, if you haven't subscribed, let me call another one.
You don't get that. I need to give away. See the last day. That one I go print the paper for.
Okay. Hello.
You don't get that now.
I don't get that. Hello. 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 I mean, the battery don't die.
No.
Ah. Don't give them one more now.
I get this.
Don't give them one
My
more.
battery don't low.
Hello. No, give them one more, I beg. Just one more.
One more.
Just one more. Give me the phone. Oh yeah. Still MTN, Abi. Which one?
Oh. Not okay. I'm gonna get it. Anything. All of them are anything.
Okay, MTN.
Just call any of these numbers. Anybody will get, I'll send out.
Okay. I don't get Michael, so just listen to my voice. The mic has died, so just listen to my voice. I'll call it twice, fast. So, fastest finger, whoever that gets it, you just come to the front. Listen. Have you subscribed? Who is active? Are you active? Now only Plutominians will understand. Are you ready? I don't know. Okay. You're looking at me. Okay. Oh yeah. Fastest finger. 526-77154-40837924. You got it. Oh yeah, come. Come now. You didn't get it. Should I call it again? Make a call up.
One now, made them no load and made them just carry the digits come out, see the number.
All right, this is what's going to happen. Due to the network issue that most of us are facing, if you get the number correctly, you can just bring your phone and then we'll know what to do by then. So just listen to the number. This one is 1,000 naira. That's why I'm not calling it anyhow. MTN. DJ, play music after the break. I should call it. You're not answering there. I should call it. I should call it. I'm not whining. Oh, look at the numbers here. 5644240927. You people are making noise now. You people are making noise. For the last time, please, I want everybody to decorum so that you hear me very well. Let me calm down. Just keep quiet. You will hear me very well. Just keep quiet. 5644240927334596. You got it. Oh yeah, come. You didn't get it. Eh? Who got it? You got it. Come again. Celebrate this guy. Some guy. Who the Zuzu? You got it again, Ramsey.
Which one you call?
Now this 96 56 56440927334596. The guy got it again. Yeah, call your number for him. Small body what? Small body what? Small body what? Don't tell anybody that it's this thing. If anybody asks, you say 1,000. Oh, yeah, go.
See, the end of the program.
All right. A little announcement. Listen, this giveaway will be happening on subsequent times. So, what you're going to do is you have to be active. You have to attend classes, and we are going to be giving out money as well. Because 2.5 is not a small money. You get so. We're going to do out giveaways. We're going to do out airtimes. We're also going to be giving out datas. So don't miss classes. We can do it after this class, so we can do it tomorrow. That's the announcement. Thank you. Bobo. Don't share and finish. Giveaway don't finish. Okay.
No play again. They come and they listen to the number.
As in, now what is supposed to be like this? Now,
You come fast. Not my 2%.
Okay. All right, ladies and gentlemen, it's about time for every one of us to settle down as the physics class will be ongoing. Remember, every distraction should be set aside. We're also going to be checking our tickets. So if you're not with your ticket, hold on to it as we go around and check. And most especially, please, please, and please, please, put aside put aside your phone because we're going to be seizing phones. They have taken the second one. Sir, are you ready? You don't die.
You want career? You think Diana?
I don't even understand the thing. Sir, are you ready? Are you ready, sir? Are you ready, sir? This one.
Easy, easy. I don't think it should be that.
No. Cover. Cover. Egbon, cover.
Funny.
I think it's the battery. Not the battery. One, two, one, two. It's not the battery. This one. This one. Maybe Kuku use this one.
It's not working with the new battery still.
It's not working.
Let's use this one for now. Make
Okay. You don't test that.
it work.
bóyá kan pe Sunday sí ìtọ́ pé máìkì ti gbé ni. The Rock fáwọn ilé ìtẹ́lẹ̀ fẹ́ ṣe nǹkan because of the heat.
We are having issue with the sound connected to this hall. So please, for every one of us to be able to hear, even at the back, we want everybody to be silent because this thing is not too loud. So please, let's make welcome the physics teacher as he comes forward to teach us. Can you celebrate, please?
So we'll be moving from not only the slide ìgbà tí wọ́n fẹ́ ṣe calculation board náà máa
No, no board, no.
so ní òkè.
You are okay. Anytime you are okay.
Okay.
I'm aligned for you.
Okay.
Sorry, there's a message for somebody. Let me make the announcement. Please, there's somebody looking for you. Apply your mom. Abayomi Demiladé, your mom is looking for you at the back, so please just go outside and check for her. Abayomi Demiladé. Then secondly, please, people at the back there, all of you at the back, come forward so that we can occupy the front seat. Thank you. Everybody at the back, come forward as I'm talking. Thank you. Be coming forward like that. Be coming forward now. Come forward. Come forward. The physics teacher loves an orderly place, so let us be ordered. There should not be space at your front. Occupy the front seat.
No, I did not say that.
Abayomi Demiladé, please go and reach your hand outside. All right. I think we're ready now. Are we celebrating again as we come forward?
Thank you very much. Oh, thank you. Welcome. Good afternoon, guys. How are you guys doing? I can see that. All right, so we're going to be looking at physics for the time being. After that, we're going to have perhaps a short break. Then we come back for chemistry and take it till. How does 8 p.m. sound? How does it sound? Sounds good, right? I'm just kidding. We're going to be rounding up by 6. All right, so. It's okay now? It's okay now. All right, so like I said, we're going to be looking at physics. There are about roughly 38 topics in the JAM syllabus for physics. I know a lot of us, if not every one of us, must have covered them, we've been taught, we have equally read them. But if you follow the pattern of questioning in JAM from year to year, there are certain areas that questions are always undoubtedly always going to come out. Questions, actually, plural, not one, not two, not three. So we're going to be focusing on certain aspects of that today, because by Monday as well, we still have physics. So whatever it is that we stop today, we just pick it up on Monday. So the very first area we're going to be looking at will be on capacitors. There is no year that questions cannot but come out from capacitor. Even though you've been taught, trust me, by the time we are going through this, you are going to see other areas that, despite the fact that you might be taught, that you might not have actually mastered very well. So, how do we talk from? How do we start from looking at what a capacitor is? A capacitor is just an electrical device. We have several electrical devices. A capacitor is one of those electrical devices that are used, among other things, for storing charges, among other things. I'm going to list other functions, other uses of capacitors. But the main usage, the main use of capacitor is for storing charges. And what about the units of capacitor? The basic unit of capacitor is farad, F-A-R-A-D. Although there are subunits of capacitors like microfarad, millifarad, picofarad, and so on and so forth. But the basic unit of capacitor is farad. Not only that, we need to talk about what are the arrangements of capacitor. Now, if you cast your mind back to current electricity, resistors are usually arranged in two ways, either end-to-end arrangement, what we refer to as series connection, or we have side-by-side arrangement called the parallel connection. The same thing goes to capacitor. Capacitor can either be arranged end-to-end. Thank you. So capacitor can also be arranged end-to-end, which is series connection, and it can also be arranged side by side, which is parallel connection. Let's have a look. So if you look at the arrangement on the board, that's obviously a series connection of capacitor, because capacitor C is connected. The end of this is connected to this end. And capacitor C is connected to the end of capacitor 3. So this is what we refer to as series connection. And when we have two or more capacitors connected in series, how do we calculate the total, or what is often called effective or equivalence capacitor? It's just opposite of what we have in resistance. So the total capacitor will now be 1 all over first capacitor plus 1 all over the second capacitance plus 1 all over the third capacitance. At least I believe we know this. I'm just building up so that by the time we begin to go into the serious aspect of it, the foundation is already laid. So this is what we have, what we refer to as a series connection. So in series connection, the total capacitance is always less than the individual capacitance. For example, if the capacitance here is 2, see microfarad, and here we have 2 microfarad, and here we have 2 microfarad. By the time we subject it to this particular formula, what we have will now be 1 over 2 plus 1 over 2 plus 1 over 2. And all we need to do is just find the LCM of them. And we know the LCM of 2 is just 2. 2 goes in 2 is 1. 1 times 1, that's 1, plus 2 goes in 2, that's 1. 1 times 1 gives us 1, plus 1 as well. And this gives us 3 all over 2. And by the time we find what our total capacitance is, that becomes 3 over 2 here. And if you cross multiply, as you can see for yourself here, 3 times CT becomes 3 CT equals 1 times 2 becomes 2. And when we divide both sides by 3, we are left with 2 all over 3. And if you look at 2 over 3, which is the total capacitance, it is less than each of the individual capacitance. That's where I'm going all along. So in a series connection, when 2 or more capacitance are connected in series, the total capacitance will always be less than the individual capacitance. If the C1 had been 2 and C2 had been 4 and C3 has been 6, the same thing will happen. By the time we calculate the total capacitance, it will always be less than each of the individual capacitance. So in series connection, the total capacitance always has a value that is lesser than each of the individual capacitance. Not only that, capacitance can also be arranged in parallel, that's side by side. So you can arrange them side by side. So this is yet another way of arranging capacitance. This time around, they are not joined end to end. They are not joined side by side. This C1, C2, and C3. This time around, you can see this, and this are all arranged adjacent to each other. And if you want to calculate the total capacitance here, we just add them together. The total capacitance will simply be C1 plus C2 plus C3. No stress there. So you will see, if you compare this with how to calculate the total resistance in current electricity, is opposite of each other. So you see the capacitance, how to calculate the total capacitance as just the opposite of what you know for the resistance. And in this case, the total capacitance is always higher than the individual capacitance. So, for example, if you assign the value for this to be 2 microfarad, and this to be 4 microfarad, and this to be 6 microfarad, by the time we calculate the total capacitance, that will be C1, 2, plus C2, 4, that's 6 already, plus C3, 6, that gives us 12. And it is evident that 12 is higher than either 2, 4, or 6. Now, if you contrast that with what we did earlier, if it is series connection, end-to-end connection, the total or effective capacitance or equivalent capacitance will always be lesser than the individual capacitance. But when they are arranged in parallel, as you can see on the board, the total capacitance will be higher than each of the individual capacitance. So please, let's take note of that. Another thing we need to talk about are the uses in details now. There are several uses of capacitance, of capacitor, but a lot of us students believe that the major thing that a capacitor is used for is just for storing charges. It does way more than that. Some of us use this in our day-to-day life. If you carry smartphones, you are using capacitors in them. So apart from storing charges, let's look at maybe 5 other functions or uses of capacitor. So we already know, everybody in this hall knows that capacitors are charge storers. They are used in storing charges. But other than that, what else are capacitors used for? So capacitor is also used in storing energy. Capacitors are used in storing energy. That's another function of capacitors. They are used in storing energy. As a matter of fact, capacitor stores energy as an electric field. So capacitors don't just store charges, they store energy as well. Number three, capacitors are used in tuning radios. Capacitors are used in tuning radios. That's another function of capacitors. They are used in tuning radio. You know what transistor radios are? When you are tuning from one station to the other, it involves that variable capacitors. And then another function, another use of capacitor is they are used in filtering out AC from AC, talking about alternating current. Capacitors are used in filtering out alternating current from direct current. Capacitors are used in filtering out alternating current from direct current, which means that capacitor will only allow alternating current to pass through it. It will prevent direct current from passing through it. So only AC passes through a capacitor. A capacitor will prevent and inhibit the passage of a direct current through it. Maybe one more. Capacitors also is used. Capacitors are used in counting machines. Capacitors are used in counting machines. If you go to banks, you want to maybe make deposits of money, for example, and you hand over the money to the cashiers there. They don't begin, especially if the money is much, they don't begin to count it by hand, one after the other. Maybe imagine you want to deposit, say, 100K, 200, or even more than that. They have counters that are there. They place it there, and then it just goes and counts it. Those counters make use of capacitors as well. And not only that, there are devices that we use at home that have timers, because we also use capacitors as timers. For example, various microwaves that we are using, you put something in it and then you put a timing in it, and after that particular time has elapsed, what happens? A sound is made. So these timers that are used in various electrical devices, they involve capacitors. And last but not the least, capacitors are used in cars to prevent electric sparks. Capacitors help to prevent electric sparks. That's an ignition of engine, because if unnecessary electric sparks do occur in cars, that can lead to fire outbreak, and we all know what can happen if fire outbreak occurs in cars. So in cars, capacitors are used to prevent electric sparks. So you can see that apart from storing charges, capacitor does way more than that. It stores energy like electrical energy or electric field. It helps in timers. It helps in filtering out alternating current AC from direct current. Not only that, it helps in tuning of radio, all these variable capacitors. And not only that, it is used in the ignition of cars to prevent electric sparks. So these are some of the uses of capacitors, apart from the fact that it is predominantly used in storing charges. So I hope that is understood. Now, let's find out what are those factors that affect the capacitance of a capacitor. There are 5 of them, so we're going to look at them one after the other. Factors that affect the capacitance of a capacitor. The capacitance of a capacitor can either increase or decrease based on these factors. So we're going to look at them one after the other. Let's start with surface area. One of the factors that affects the capacitance of a capacitor is the surface area of that particular capacitor plate, of the plate. Now, capacitance, let's wait a moment. capacitance always varies directly with the cross-sectional area. So as you can see from the board, as the area of the plate increases, so also does the capacitance also increase. So when the area of the plate increases, the capacitance also increases, because you can see the relationship between them is a direct relationship. Capacitance is directly proportional to the cross-sectional area of that particular plate. So the larger or the higher the surface area, the higher the capacitance. And if you are wondering, why does the capacitance increase as the area of the plate increases? Because when the area of the plate increases, it allows for more electric lines of force to actually to be stored in it. The larger the area, the higher the amount of electric lines that can be stored in that particular plate. And the larger the electric line stored in that plate, the higher the capacitor. So the number one factor we just finished looking at is the area of the plate. Number two is the separation of the plates. The separation of the plates. Let's assume we have two plates like this. If this a plate, this is a plate. Now you can see the distance between them. Now consider another plate like this. This time around, look at the distance between them. It is obvious that the distance between these two plates is smaller here, but the distance between these two plates is wider here. So the distance between the two plates also matters, just like the area of the plate matters. But this time around, the way the distance between the plate affects the capacitance is opposite to that of the area. Don't forget, as you can see from the relationship between the capacitance and the area, the higher or the larger the area of the plate, the higher the capacitance. But in case of the distance between them, the wider the distance between the two plates is, the lower the capacitance. So it is an inverse relationship between them. So which means capacitance is inversely proportional to the distance between the plates. What does that mean? It means that when the plate, take a look at this, when the two plates are closer here, there's going to be higher capacitance there. But when the two plates are wider from each other, the capacitance there actually decreases. So the closer the plates are to each other, the higher the capacitance. But the wider the two plates are from each other, the lower the capacitance. And if you are wondering why that is so, when the plates are close to each other, that makes the electric strength between the plates to be higher. And the higher the electric strength, the higher the capacitance. But when the plates are wider from each other, that reduces the electric strength between them, and the lower the electric strength, the lower the capacitance. So when you are looking at or considering the effect of distance on capacitance, the higher the distance, the higher the value of D, or the wider the plates are from each other, the lower the capacitance. But the closer, which means the distance is small or low, the closer the plates are to each other, as you have it here, the higher the capacitance. So the capacitance here is going to be higher, while the capacitance here is going to be lower. As you can see here, is an inverse proportionality. So capacitance will only increase when the value of D is small, whereas capacitance will decrease when the value of D is high. So we have two factors now. The first one was the area, which is a direct proportionality, which means that the capacitance will increase as the surface area increases. And we just finished looking at the distance between them. When the distance between them is very, very small, the capacitance increases. When the distance between them is wider, the capacitance decreases. Let's look at the third one. The third one is the nature of the dielectric substance. The nature of the dielectric substance, or you can say the nature of the dielectric material. Now, dielectric materials are those substances that can sometimes be inserted in between the plate. Look at this. This space can either be occupied by air, which means it is a free space. The same thing, this space can also be occupied by air, or you can occupy it with a dielectric material. And first thing you need to know here is dielectric. When you insert a dielectric material in between the two plates of a capacitor, that has a direct proportionality with the capacitance, which means that when we place any dielectric material in between the plate, it will bring about an increase in the capacitance of a capacitor. For example, let's assume we come across a question like this. Introducing a dielectric material into a gap between two capacitor plates will A, increase the capacitance, B, decrease the capacitance, C, first increase the capacitance and then decreases the capacitance, and so on and so forth. When you introduce a dielectric material in between the two plates of a capacitor, it will always lead to an increase in the capacitance. If there are no dielectric material in between the plate, it means that particular plate is filled with air. The capacitance will be lower. But when you introduce any dielectric material in between that particular plate, introduction of dielectric material always have one effect on the capacitance, and that is to increase the capacitance of that particular capacitor. So, which means that the relationship between the capacitance and the dielectric material is a direct relationship. So you can see as the capacitance increases with the introduction of a dielectric material. Now, we're not done with that. What kind of material can be used as a dielectric material? Because not every material can function as a dielectric material. Before a material can be used or can be said to be a dielectric material, it must either be an insulator or a substance of low conductivity. We do not use metals. You know, metals are good conductors of electricity. Metals cannot be used as a dielectric material. As a matter of fact, most of the time, we use materials that are either completely insulators. You guys know what insulators are. Insulators are those substances that prevent or that do not allow the passage of charges or electric current through them. So examples of those materials are going to be things like a glass, right? Things like ceramic, for example, plastics, all right? Mica, M-I-C-A. So these are examples, let me say them again. Examples of solid dielectric materials are examples of solid dielectric materials are, we have mica, M-I-C-A, we have ceramic, we have plastics, we have glass. So all these are examples of dielectric materials. And if you look at them, you will see that they are insulator. They do not conduct or allow electric current or charges to pass through them, because that is what a dielectric material should be made up of. So you can come across questions asking you that the following can be used as a dielectric substance, except all you have to do is look for the option that contains a good conductor of electricity. Any metal cannot be used as a dielectric material because one of the characteristics of metals is they are good conductors of electricity. A good conductor of electricity cannot be used as a dielectric material. Now, I don't want you to believe or to think that the only material that can be used as a dielectric substance will be in solid form. No, we can have dielectric substance in the three common states of matter. We can have them in solid state, we can have them in liquid state, we can have dielectric material in gaseous state. I've given you like 4 examples of dielectric materials in solid state. I've given you glass, I've given you ceramic, I've given you plastic, I've given you mica. Not only that, what about dielectric material in liquid state? All right. Distilled water is an example of a dielectric substance in liquid state. So, an example of liquid dielectric substance is distilled water. Now, pay attention. Not just any water, distilled water. You guys are chemistry students. Another name for distilled water is deionized water. Because remember, what are the charge carriers in electrolytes or in liquid form? They are the ions, isn't it? So when you say distilled water or deionized water, deionized means that the ions have actually been removed. So which means that they are now almost completely a non-conductor of electricity. Because water, normal water that are not distilled water, don't forget distilled water are the purest form of artificial water. All right. So if it's normal water or maybe water that contains little amount of acid, is not going to be able to be used as a liquid dielectric substance because it is going to be a conductor of electricity. But distilled water is completely deionized. All the ions in it are removed. Distilled water is almost completely a non-conductor of electricity. And like I've told you at the beginning, before any material could be considered to be called or to be used as a dielectric material, it must be a non-conductor or it must be a very poor conductor of electricity. What about gases? Can we have gaseous dielectric material? We can. Gaseous, if you want to put examples down, examples of gaseous dielectric substances are number 1, dry air. Air, dry air. Now let's stop there for a moment. I did not just say air because air can either be dry or it can be damp. Damp means that it is moist. Moist air can conduct electricity. As a matter of fact, that's one of the reasons why it is dangerous for you to handle electrical devices that are plugged in when your hands are moist or wet. So damp air is not an example of a gaseous dielectric substance, but dry air is. So dry air is one example. Another example is nitrogen gas. Nitrogen is another example of a gaseous dielectric material. And not only that, noble gases like helium. Helium is also another example of a gaseous dielectric substance. So here you have them. Let's recap. Dielectric substances, how do they affect the capacitance of a capacitor? They increase the capacitance of a capacitor. When you introduce a dielectric material in between the gap between the two plates. This one plate of the capacitor, this another plate. The gap in between them, when you introduce any dielectric material into them, that will correspondingly increase the capacitance of that particular capacitor. So introduction of a dielectric material will lead to an increase in the capacitance. You can see the direct proportionality here. And another thing I did mention was that not every material can be used as a dielectric substance. Only insulators or very poor conductors of electricity can be used. And I told you that dielectric substances can be in solid state. I give examples of solid dielectric materials such as glass, such as ceramic, such as plastic, and mica. Not only that, I told you it can be in liquid state. An example of the one that is most common is distilled or deionized water. And finally, Examples of gaseous dielectric substances are nitrogen gas, helium, which is a noble gas, and also we can have dry air. So now these are three factors now. We consider surface area, which increases. When surface area increases, the capacitance increases. We've spoken about the distance between the plate. As the distance between the plate increases, the capacitance, on the other hand, decreases, and vice versa. And then we've spoken about the dielectric substance. Now, let's move ahead and talk about the fourth one. The fourth one, permittivity of the free space. Permittivity of the free space. Permittivity of the free space. Now, permittivity of a free space is a physical constant. It is usually denoted by this. You guys have seen this several times. It's denoted by, that's the symbol of permittivity of the free space. It is a constant. A constant means that the physical constant, the value doesn't change. It's just like a Planck constant. A Planck constant will always have a value here in Nigeria and all over the world. The value of Planck constant will always be 6.636 times 10 to the power minus 34 joule second. The same thing, permittivity of the free space is a constant, a physical constant. It does not change, but the capacitance of a capacitor is directly proportional to that permittivity. So which means that the capacitance is directly proportional to the permittivity of the free space. So if you look at them, out of the four now, three of them always have direct proportionality with the capacitance. Which are the three of them? The area. The larger the area of the plate, the higher the capacitance. What about the dielectric constant? The introduction of a dielectric constant, the higher the dielectric constant that is introduced, the higher the capacitance. And the final one is the permittivity of the free space, which is a physical constant. When you introduce this permittivity of the free space material into the gap in between the two plates, that increases the capacitance. And if you join all of them together, if you combine all the four factors together, we are going to have something like this. So we're going to have C is equal to E naught ER A all over D. And this is a formula a lot of you have seen. At times, this E naught and ER are simply written as E because E is equal to E naught times ER. So, which means the capacitance is directly proportional to the permittivity of the free space. Capacitance is directly proportional to the dielectric material between the plate. Capacitance is directly proportional to the area of the plate. And finally, capacitance is inversely proportional to the distance between the plate. So before I leave this, let's recap. Out of these four factors, three of them will lead to an increase in the capacitance. And the three of them are the area of the plate. As the area of the plate increases, the capacitance increases. As the distance between the plate increases, the capacitance decreases. But as the distance between the plate decreases, the capacitance increases. When you introduce a dielectric material in between the plate, that leads to an increase in capacitance. And finally, the permittivity of the free space also brings about an increase in the capacitance of a capacitor. So that settles that. Another area, as a matter of fact, the last area we need to look at is how do we figure out? I told you earlier that one of the functions of a capacitor is to store energy, isn't it? So how do you calculate the amount of energy stored by a capacitor or by several capacitors that maybe are connected in series or are connected in parallel? Now, there are various formulae or formulas, if you will, that are used, three of them actually, that are used in calculating the energy stored in a capacitor. I'm pretty sure you are familiar with them, but nonetheless, let's look at the various formulas that we can use depending on what the questions are. The three formulas or formulae that we can use to calculate the energy stored in a capacitor are: the first one, energy is equal to half CV squared. E is the energy stored in the capacitor. C is the value of the capacitance in farad. Now, I cannot stress that enough because the capacitance can be given in microfarad. You cannot use that in microfarad. We are going to have maybe one or two examples for you guys to exercise with. So, if the capacitance is given in any other unit other than farad, it is our duty to ensure that it is first of all converted to farad, and then we move on to the last one, which is the V, the potential difference or the voltage across the capacitors. That voltage can also be given in millivoltage, in which case you have to divide by 1000 to convert it to voltage. It will be given in kilovolt, in which you want to multiply by 1000 to convert it to volt. So when are we going to make use of this formula? When the question is asking us to calculate the energy, and then we have been given the capacitance, and we have been given the potential difference. But at times, we might not be able to use this. We might need to use this one instead. Half QV. This is another one. So if a question is asking us to calculate the energy stored in a capacitor, and we are given the charge, that's Q, in coulomb, that's the unit of charge. We know that. You are given the charge in coulomb, or we are given the charge in microcoulomb, because the charge could be given in microcoulomb as well. If the charge is given in microcoulomb, what do we do? How do you convert from microcoulomb to coulomb? We just multiply by 10 raised to the power minus 6, which means that if we are given a charge to be 2 microcoulomb, this one becomes 2 times 10 raised to the power minus 6 coulomb. The same thing applies to capacitors. If I given C, a capacitor now to be 5 microfarad, we can't use it like this, like I've said earlier. It now becomes 5 times 10 raised to the power minus 6 farad. So please ensure that when you are given either the charges or the capacitance in microfarad, ensure it is converted to farad before you calculate or you carry out any calculation. So we're going to make use of the formula 2. If we are asked to calculate the energy, but this time around we are given the charge either in coulomb or in microcoulomb, and we are also given the voltage or the potential difference across its end. And then there is number 3, the third one. We can be given a question to calculate the energy stored, but this time around we will now be making use of this. So there is another one, which is number 3, which we are looking at, half Q squared over C, which means this formula, the third formula here, will be used when we are given two things. When we are given the charge either in coulomb or in microcoulomb, or you are given the capacitance either in farad or in microfarad. Like I've told you, if you are given a microfarad, it is your job to ensure it is first converted to farad before it is used. So let's take a look at the 3 of them. The first one, once again, the first formula will be used when we are given 2 parameters in the question. The capacitance, it could be just one capacitor, which means you just make use of that straight away. But at times, it could be 2 or more capacitors. They will tell us either connected in series or connected in parallel. For example, imagine the question that says, calculate the energy stored in 2 capacitors of capacitance 2 microfarad and 4 microfarad connected in parallel. If the potential difference across the end is maybe 50 volts. This time around, we are given two capacitors and we have been told how it is connected. And I've shown you how to calculate the total capacitance either in series or in parallel. So if you are given two capacitors now and we are told it's connected in series, all we have to do is say 1 all over whatever the capacitor plus 1 all over the other capacitor. And you do what needs to be done. But if you are given in parallel, what do we just do? We just add them together. That becomes our C in the first equation. And then we multiply that by the square of the potential difference and we divide everything by 2 because that's what the half here means. Number 2 is going to be used if we are given the charge either in coulomb or in microcoulomb, and we are also given the potential difference or the voltage across the end. And then number 3 will be used when we are given the charge and we are given the capacitance. So if you take a look at the 3 formulas, you will realize that there are only 3 factors here. There are only 3 things here that can affect the amount of energy stored by the capacitor here. The 3 things are the capacitance C, the voltage V, and finally the charge. The charge is here, so I don't need to talk about the charge here. They mean the same thing. Once again, you can come across questions asking you that which of the following affects the energy stored by a capacitor. There are only 3 factors or 3 things that can affect the energy stored by a capacitor. Please do not confuse that with the factors that affect the capacitance of a capacitor. No, we're talking about the factors that will affect the energy stored by a capacitor. And those factors are just 3. They are evident from the formula. The capacitance is one of them, the charge is one of them, and also the voltage is one of them. As you can see here, you can see that the energy is directly proportional to C. What happens? The higher the capacitance, the higher the amount of energy that will be formed, that will be stored, rather. And then you can see that Q, energy is also directly proportional to the charge, which means that as the charge increases, the energy stored will also be increased as well. So let's take note of that. That's talking about this and talking about this. So at times it could be more. Why don't you see for ourselves? Let's look at some slides and let's look at some slides on capacitors. On capacitors, please. Okay. All right. So, okay. Thank you. So let's look at this. All right. So let's take a look at this. It says if a 10 microfarad capacitor is charged to 100 volts, how much energy is stored? You guys should be able to figure this out. Take a look at the question and let's look at the board. Which of the 3 formulas would be useful here based on what we are provided? Which of the formulas? The first one, because you can see the capacitance has been given C, which is 10 microfarad, but don't forget, you cannot make use of that particular 10 microfarad the way it is. What do? We convert it to farad by doing what? By multiplying it with 10 raised by minus 6. And we have been given the voltage as well. So I know you guys are already working on it. So let's see what the answer will be. Okay, so what do we have? We have capacitance to be 10 microfarad. If you are converting this 10 microfarad to farad, it becomes 10 times 10 raised to the power minus 6 farad. And this one, if you multiply 10 to the power minus 6 by 10, it becomes, okay, we can leave it like this. So our V, the potential difference V is 100 volts. So our energy E becomes 1 over 2 CV squared. That's 1 all over 2 times the capacitance. We've gotten that to be 10 times 10 raised to the power minus 6 times the voltage is 100. But we have to square it. So that becomes 100 all squared. So this gives us 1 over 2 times 10 times 10 to the power minus 6 times, if we square 100, that gives us 1 times 10 raised to the power 4, doesn't it? That should be 10,000. And 10,000 converted to standard form should be giving us 1 times 10 raised to the power 4. So the energy here becomes 1 over 2 times, don't forget, this particular 10 can be written as 10 raised to the power 1. I hope you know that. So it becomes 10 raised to the power 1 times, this is 10 raised to the power minus 6 times, forget about the 1 here. Anything multiplied by 1 or divided by 1 stays the same. Then times 10 raised to the power 4. Everything in joule. And this one gives us 1 over 2 times, since this is 10, the base are the same. So you can use law of indices to add all the powers together. That's going to be 1 plus minus 6 plus 4. 1 plus 4 gives us 5, right? And then 5 plus minus 6 here gives us what? That's right, minus 1. And then we know that minus this is going to be 1 over 2 times 10 is power minus 1 is the same thing as 1 all over 10. We all know that from indices. So this gives us 1 all over 2 times 10. That's going to be 20 joule. So what is 1 divided by 20? So 0.05. So you can see from there. That's easy. Do you understand that? Okay, so that's for that. What? Say that again. We did not what? What about 1 over 2? The 1 over 2 is here. Times 10 to the power minus 1 is 1 all over 10. 1 times 1 is 1. 2 times 10 is 20. So once again, we know the capacitance is 10 microfarad. That is air. 10 microfarad converted to farad will be 10 times 10 to the power minus 6. That's farad. The voltage, as you can see, is given as 100 volts, which is here. And when substituting into the formula here, that's 1 over 2 times the capacitance, which is 10 times 10 raised to the power minus 6. That's what we have here, times the square of the voltage. That's 100 squared. And that's what we repeated here. 100 squared is 10,000. 10,000 converted to standard form gives us 1 times 10 to the power 4. Now, coming here, 1 all over 2 times this 10 here can be written as 10 to the power 1. 10 to the power minus 6, that's what they have here. Then this 1 times 10 to the power 4 is the same thing as 10 to the power 4 because 1 multiplied by anything remains the same. So since this is 10, 10, 10, they all have the same base. So in indices, when the base are equal, we can add all of them. We can add all the powers together. The power here is 1 plus this. That's going to be minus 5 plus 4. Minus 5 plus 4 is going to give us minus 1. That's what we have here. And then 1 all over 2, that's 1 all over 2. 10 is by minus 1, the same thing as 1 all over 10. It's just like in indices. In indices, x raised by minus 1 is the same thing as 1 all over x, isn't it? So the same thing. 100 raised by minus 1 is 1 all over 100. So 1 times 1, that's 1. 2 times 10, that becomes 20. And 1 divided by 20, that gives us 0.05 joules. So I believe it's clearer to us now. So let's take a look at the second one, please. So let's look at this. Now, I just told you here the last time that there are 3 factors, there are 3 things that affect the energy stored by a capacitor. What are they? The capacitance, the voltage, and the charge. This time around, they are asking us what will happen to the energy when one of those things is changed. So let's look at the question. It says doubling the voltage across a capacitor will multiply the energy stored by dash. So let's take a look at the board. We still remember this formula that we just made use of. Let's look at this. So this, because this is talking about the relationship between the energy stored and the voltage. This is the energy stored and this is the voltage. So what is the relationship between them? You can see from here that energy is directly proportional to what? To the scale of the voltage. Do you understand this? Exactly. So what do you think happens? Now, if we increase, because it says doubling the voltage, if you increase that voltage by a factor of 2, what will happen to the energy here? Because that's what it's asking. Doubling the voltage across the capacitor will multiply the energy by that. Since you have scale here, when we double this one, see, here now becomes, if you double the voltage here, it now becomes 2V everything squared. And then here you now have E, 2 squared, that's 4. And then V squared. Now compared here with this, what is the difference? 4. So the energy is going to increase by a factor of 4. If you don't want to do it that way, if you are the type who love having formulas for everything you do, it works as well. All you have to do is this. You just establish the fact that E is directly proportional to V squared. If you introduce a constant here, it becomes E is equal to KV squared, where K, of course, is a constant. And this particular K now, we can now become E all over V squared. So we can convert this one to be E1 all over V1 squared is equal to E2 all over V2 squared. Do you guys understand this research? And then we can now put the parameters we are given in the question in there to figure out what it will be. So the question says doubling the voltage. Doubling the voltage means that increasing the voltage by a factor of 2. If the voltage is doubled, it means that the second voltage will be twice of the V1. Do you understand this relationship first before we move on? That's the meaning of doubling the voltage. When you double something, you multiply it by 2. You increase it by a factor of 2. So if you are doubling the voltage, it means that the second voltage is going to be twice of the initial voltage. In that case, what would then be the relationship between the E1, initial energy, before doubling it, and the E2 after you've doubled it? So here, this is our E1 is here, all over our V1 squared is here, is equal to E2 all over the V2. Now, don't forget, V2 is here. That's going to be 2V1. Don't forget, it's squared. So everything is squared. Then this E1 all over V1 squared is equal to E2. Don't forget, it is this E2 we are looking for. All over 2 squared, that's 4. V1 squared, that's V1 squared. All we need to do now is make this particular E2 the subject of the formula. If we do that, our E2 will become E1 times 4 V1 squared. E1 times 4 V1 squared divided by V1 squared. That's V1 squared. V1 squared cancels V1 squared. Look at what is remaining. E2 now is equal to 4 times E1. That's 4E1. So you can see that the energy stored now increases by what factor? By a factor of 4. At times in JAM, instead of giving maybe 2, 4, and so on and so forth, they can use terms like doubled, quadrupled, halved, and so on and so forth. So when you say something has been increased by a factor of 4, it means the value has quadrupled. Is that understood? If it has decreased by a factor of half, like option D there, it means the value has been halved. So please, let's take note of that. So as you can see now, when we double the voltage across a capacitor, it will lead to the energy stored to be quadrupled, increased by a factor of 4. I hope this one is understood. Let's look at the third one. So the energy stored in a capacitor is independent of, now what is the meaning of the word independent? Is not affected, does not depend on. These are the terms you can use in place of independent. When I was explaining, I've told you the 3 things or the 3 factors that affect the energy stored by a capacitor. So let's take a look at it. The energy stored in a capacitor is independent of A, the capacitance, B, the voltage, C, the charge, and D, the resistance. Which one will be the correct answer here? The resistance. Resistance has no place here. Because if you look at the 3 formulas or formulae that are given you for calculating the charge stored in a capacitor, none of them have resistor, isn't it? The first one we consider was E is equal to half CV squared. It contains C, capacitance, and V, voltage. The second one was E is equal to half QV. It contains Q, the charge, and V, the voltage. And the third formula is E is equal to half Q squared all over C. It contains the charge Q and the capacitance. So the resistance has no effect whatsoever on the energy stored. That is the meaning of the word independent. Is not affected, does not depend. Let's take a look at the fourth one. Okay, so it's getting interesting now. So let's look at this. What happens to energy stored if a capacitor is connected in series with another of equal value? What happens to energy stored if a capacitor is connected in series with another of equal value? Let me give you a few seconds to figure it out. Then we come back together to the slide and figure it out. So I'm giving you a few seconds to figure it out, and if you have, you can tell us if a capacitor is connected in series with another capacitor of equal value. So say you have a 2 microfarad, then it's connected to another capacitor of equal value, 2 microfarad again. The question is asking, what happens to the energy stored? Will the total energy double, which means increase by 2? Will total energy be halved, which means decreased by 2? Will total energy remains the same, or will the total capacitance double? As a matter of fact, you know, we are talking about what happens to the energy here. Everybody in this hall knows that answer D, option D, can never be even considered at all, because the question doesn't have anything to do with what happened to the capacitance. So the answer is going to be A, B. So what will it be? It's going to be halved. That's very good. Because I've told you at the beginning that when you connect resistance in series, what happens to the total resistance? It is lower when you are connecting that particular capacitor with another capacitor in series. That will reduce the total capacitance. So it's going to have the energy stored. That's very good. Let's go to the last one, the 5th question now. Let's go to the 5th one. Okay, if a capacitor is disconnected after charging, what happens to its stored energy? After all, I've told you, among other things, that a capacitor is used for storing energy like electrical energy or electric field. So if you charge a capacitor and then haven't charged it full, you disconnected the capacitor from the electric supply. So what happened to the energy that had been stored in that capacitor? Will the energy be lost immediately after disconnecting it? Will the energy remain stored in that capacitor? Will the energy be converted to it, or does the energy increase? Anyone? Exactly. When you charge a capacitor, it does not matter if you disconnect it and you leave it there for a year. Once that particular capacitor has been charged, the energy stored in it will remain stored there. It doesn't discharge. It doesn't make disconnecting the capacitor after charging it does not make it to lose the energy. It will not add to the energy stored. It will not decrease from the energy stored. So the energy stored will not be converted to it at all. So there is no conversion of energy in a capacitor. The last one, let's take a look at the last slide now. Okay, so a capacitor is used for which of the following? A, for storing energy. B, for preventing electric sparks. C, for filtering out AC from. Okay, so now let's be honest. Let's assume that I had started today's class with this slide. How many of you have been so confident the way you are now on which of them? How many of us know that a capacitor is used in filtering out AC from DC? Few of us, exactly. So that's the beauty of it. So now you know that apart from storing charges, because that's what a lot of us know that capacitors are used for. You also know that it is used for storing energy, it's used for preventing electric sparks, especially in the ignition of engines of cars. It is used also in filtering out AC, because the capacitor will only allow AC to pass through it. It will prevent DC from passing in. And also, it is also used in tuning of radios. Don't forget, it is used as timers in electrical devices as such. So that's for that. If you have any question on capacitor before we switch to AC circuit, now will be the time to ask your question. Do you understand what we have done so far? Okay, so let's switch our attention now to alternating current circuit, because that's an area that you can't but run into questions. You can't but encounter questions. So let's revise and see how well we still remember alternating current circuit. Now, it's a good thing that we've already spoken about the fact that capacitor can be used to filter out AC from DC, which means we have two main types of current. We have the direct current, that's the one that cannot change its direction, and then we have alternating current, the one that can change direction. Even though you can convert one current to the other. For example, we can convert AC to DC, isn't it? By using a rectifier like a diode, isn't it? We know what rectifier is. A rectifier is something like a semiconductor, like a diode, that can be used to convert an alternating current to a direct current, that can be made to convert or restrict alternating current to move in only one direction. So if a rectifier can be used to convert an AC to DC, is it possible to convert DC to AC? What do we use? So that again? Inverter. That's very good. So the two of them can be interconverted to each other. We can convert a DC to AC by using an inverter. We can convert an AC to DC by using a diode, which is a rectifier. Now, let's talk about alternating current. Alternating current, like I've said, is that type of current that can move in different, that can change its direction. we say it moves sinusoidally. That is, it increases to a maximum, comes back to zero, goes down, comes up, and just changes its direction as it goes on. And the kind of current that we are supplied with by government, PACN, is an example of AC circuit. Because it's only AC circuit that can, it's only AC current rather, that can be stepped up or stepped down. That's one of the advantages of alternating current over direct current. Now, the electricity we're using here is produced probably in Niger State or any of these generating stations. When the power is generated, they have step up transformers in those stations that steps up the voltage, and then the current is now passed, the power is now passed at a high voltage and low current. In physics, we refer to it as high tension transmission, isn't it? Power is often transmitted at a high voltage and low current. Power is never transmitted at a high current and low voltage, because if you do that, guess what will happen to the electric cables? What happens? They become hot, isn't it? They can even snap, they can cut. So to prevent overheating of the electrical cable or to prevent loss of electrical energy in form of heat, that's why we always transmit electrical power at a high voltage and low current. That's by the way. So this AC current, this alternating current we're talking about here, can change its direction as it flows about. And several areas of interest that questions always come in JAMB in this area are the relationship. There are several formulas here. So you need to be very acute and aware of them. There are several of them. You have formulas relating the root mean square value of current with the maximum or the peak value of current. We all know that, right? The root mean square value of current, IRMS, is equal to the peak value of current all over root 2. Because one of the problems that students often have in this area are how much the formulas are. So the root mean square value of current is equal to the peak value of current all over square root of 2, or we can simply say the root mean square value of current is equal to 0.7071 I naught. If you are wondering, because at times that is how JAMB puts this. If you are wondering how does it transform to this? This is how. This one can be written as this. You can write it as I naught times 1 all over square root of 2. And if you pick up your calculator and find 1 all over square root of 2 to 4 decimal places, what does it give us? That's that. So apart from this, this is another relationship between the root mean square value of current and the peak or the maximum value of current. The same thing applies to the voltage as well. You can say that this is V RMS, and then this is going to be the peak value of the voltage. We can apply the same thing to this, and then the same thing with this. So please take note of that. Other areas that they can ask questions like that, they can ask you that what is the ratio between the root mean square value of current and the peak value of current? What does that mean? They are looking for ratio like this. The ratio between the root mean square value of current and the peak value of current. And you can easily get it from here. After all, we know that IRMS is equal to the peak value of current all over square root of 2. Which means that if we bring this one here, we can now have IRMS all over I naught is equal to 1 all over square root of 2. Don't forget, the ratio of RMS to that of peak value can be written as IRMS all over I naught. After all, in mathematics, if you say X ratio y is equal to 1 ratio 2. We can write it as x all over y is equal to 1 all over 2. So that's that. So if you ever come across a question asking you for the ratio between the ratio of the root mean square value of current or voltage to the peak value of current or voltage, that would be 1 ratio 2. So this becomes 1 over root 2 becomes 1 ratio square root of 2. That's one area. Another area we need to talk about now are areas involving reactance. Now, what is reactance? Reactance is often defined as the opposition to the flow of an alternating current by either a capacitor or an inductor or both. Once again, reactance is defined as opposition to the flow of an alternating current by a capacitor or an inductor or both. So, a capacitor, we've spoken about capacitor. Capacitor is measured in farad, like I've said earlier. So, we can have an alternating current circuit containing only capacitor. So, if you want to find the reactance of that particular circuit, we are going to call it capacitive reactance. That is reactance of an AC circuit containing only capacitor. And the reactance of a circuit containing only capacitor is given as this, XC, which is equal to 1 all over 2 pi FC. That is another formula you need to be conscious of. Pi had the same unit in as mathematics, either 3.142 or 22 over 7. The F here is the frequency, which can be given in hertz or it can be given in form of pi. And then the C here, you already know, is the capacitance, which should be in farad. If you are given a microfarad, it is your job or duty to ensure it is converted to farad. And as you can see here, the capacitive reactance, XC, is inversely proportional to the frequency here, which means that XC is inversely proportional to the frequency. As the frequency increases, the capacitive reactance actually decreases. Is an inverse proportionality between the two of them. Another area that questions are also very common here is the relationship between the current and the voltage in a capacitive circuit. Now, in a capacitive circuit, in an AC circuit that contains only capacitor, the current leads the voltage by pi over 2. Let's take note of that. In a capacitive circuit, the current leads the voltage by pi over 2. Pi over 2 means that pi over 2, that's in radian. But if you want to convert it, that's going to be 90 degrees. So in a circuit that contains only capacitor, the current leads the voltage by 90 degrees or pi over 2. Let's take note of that. And what about the reactance we're talking about? What is the unit of reactance? Ohms, right? Exactly. Reactance are the same unit as resistance. It are the same unit as impedance, which we are going to talk about much later. So that is for that. Apart from capacitive reactance, we can also have an alternating current circuit that has only inductor. Inductor is represented by capital letter L. And the unit of inductor is what? What is the unit of inductors? Henry. It is usually denoted or represented by capital letter H. So, if you have a circuit that contains or possesses only an inductor, the inductive reactance will be represented by bits. The inductive reactance becomes XL is equal to 2 pi FL. So it's a direct proportionality all through. XL, inductive reactance, is equal to 2 pi FL, which means as the inductance increases, the inductive reactance will increase. As the frequency increases, the inductive reactance also increases. And not only that, in an inductive circuit, that is, in a circuit that contains an inductor, the current lags behind the voltage by 90 degrees. Now let's put that side by side with what I said when we're talking about that of capacitor. In a capacitive circuit, in a circuit that contains capacitor, how does the current and the voltage, how did they behave? Are they, which one leads? The other one, the current leads the voltage by what? By pi over 2 or 90 degree. But if it is an inductive circuit, all right, it is now the current that lags behind the voltage by 90 degrees. At times in JAM, they represent this information in form of diagrams. So that's why you need to know them. If you want to say that the current leads the voltage by 90 degrees, you can represent it like this. So that's that. So in a particular capacitive circuit now, the current leads the voltage by 90 degrees. You can see the angle between them. So since the current is leading, it points upward like this. But in an inductive circuit like this, in an AC circuit containing only an inductor, the current lags behind the voltage by 90 degrees. I'm going to have something like this. So you can see the difference. So this represents an inductive circuit where the current is lagging behind. That's why it points downward. The voltage by 90 degrees, whereas this represents a circuit, a capacitive circuit, in which the current is leading the voltage by 90 degrees. So you should be able to know which of these diagrams, because at times you could be given 4 diagrams like this, and then they ask you which of the following diagrams represent a capacitive circuit. A capacitive circuit is when the current is leading the voltage by 90 degrees. An inductive circuit is when the voltage is lagging behind, the current is lagging behind the voltage by 90 degrees, or the voltage is leading the current by 90 degrees. So please, let's take note of that. Another area we are going to look at now is talk about the impedance. I told you earlier that reactance is the opposition to the flow of an alternating current by either a capacitor, an inductor, or both. How about an impedance? Impedance is the overall, is the effective, is the total opposition to the flow of an alternating current offered by a resistor or an inductor or a capacitor or both, which means that a reactance talks about either capacitance or the capacitor. But if I think about impedance, impedance talks about either combination of resistor and the capacitance, or combination of the resistor and inductor, or combination of the resistor, the capacitance, and also the inductor. What I'm trying to say is, if I think about an impedance, let's take a look at this. Impedance can have 3 formulae. Impedance can be represented by this. So look at this. So this is impedance. Impedance can be calculated by finding the square root of the current of the resistor plus the inductive reactance. So which means that impedance can be gotten from the combination of the resistor and the inductive reactance. Impedance can also be gotten from the combination of the resistor and the capacitive reactance. And still, we can get impedance from the combination of the three of them. We can also have this. We can have impedance calculated by finding the square root of this. So which means that impedance can equally be calculated by finding the difference between the inductive reactance and capacitive reactance, and then we now take a square of that and add it to the square of the resistor. That is why we define impedance as the overall, the total, the effective resistance to the flow of an alternating current in an AC circuit that has a combination of either the resistor and the inductor, the resistor and the capacitor, or a combination of the resistor, the inductor, and the capacitor. So we are supposed to be able to remember all these formula so that if the need arises and we are asked to calculate the impedance in a circuit that contains the resistor and an inductor, we know the first thing we need to do is calculate our inductive reactance. And we know the formula for that already, 2 pi FL. And after that, we just plug it into this particular formula. Or perhaps we are asked to calculate the impedance of a particular circuit that contains a resistor and a capacitor. What we need to do is calculate the capacitive reactance, which we know the formula already. XC is equal to 1 all over 2 pi FC. And then we just plug it in here. Or perhaps we are given an RLC circuit. RLC stands for R, resistor, L, inductor, C, capacitor. In which case, we are going to make use of this, a combination of the resistor, the inductor, and the capacitor. And the three of them are related by this graph right here. So this is the relationship between the inductive reactance XL, capacitive reactance XC, and the resistor. As you can see here, the inductive reactance and the capacitive reactance are completely out of phase. And if you want to calculate our impedance now, we do this. Now, this is the impedance. And if you look at this, all you have to do is just bring this down here. It's just like when we now have a right angle triangle. From here to here, it's like this to this. That becomes our, don't worry, you come back there. So the angle here, by the way, let me talk about that, will be what we refer to as the angle of lead or lag, also called the phase angle. So if you want to calculate the Z here, the impedance, what do? We subtract the XL here from the XC here. So which means the opposite here, because the angle faces here, the opposite becomes XL minus XC. And we know the adjacent here is R, you can see. And then the hypotenuse is the Z. That's actually where this formula came from. Because if you consider this triangle now, this whole triangle here is now a right angle triangle. And if we use the Pythagoras theorem, I want to find our Z here. The Z will become Z squared, that is square of the hypotenuse, is equal to the square of the opposite plus the square of the adjacent. So the square of the adjacent here plus the square of the opposite, which is XL minus XC all squared. And you know what happens if I want to find the square root of both sides now, then the square root of Z squared become just Z. And then the formula that we had before comes out of that. Where am I going with this? This is where I'm going all along. This particular angle here, we refer to it as the phase angle. There are various formulas that we can use to calculate the phase angle. One of such is to say that tan of the phase angle is equal to R all over Z. We know from simple trigonometry that where the angle faces is the opposite. Here, that's the adjacent. Here, that's the hypotenuse. So if you want to find tan of this, that becomes, don't forget, SOHCAHTOA. So tan is going to be opposite, that's XL minus XC all over the adjacent, which is going to be R. Or if you want to find cos of it, the cos of the phase angle, because it's going to be important when we get to the power, the cos of the phase angle now becomes adjacent R all over the hypotenuse, which is Z. So all these formulas are very, very important, and the diagrammatic representation, because at times questions come from diagrams. They'll give you some vectorial diagrams. What I drew here, that's what they call vectorial diagram. They ask you which of the following vectorial diagrams describes an AC circuit, maybe at resonance or so on and so forth. So you should be able to know that the XL, the inductive reactance, is always at the positive aspect of the Y. The plus Y here, the capacitive reactance is always on the negative Y, and then the resistance is always on the positive X axis. And that particular angle between that impedance and the resistor, we refer to it as the phase angle. And the phase angle have different values, except when we get to resonance, because at resonance, the phase angle now remains constant. It's going to have a particular angle. We're going to get to that when the time comes. So let's recap what we have done so far. We spoke about the fact that reactance is measured in ohms. We spoke about the fact that we have two types of reactance: inductive reactance, that's the opposition to the flow of an alternating current offered by an inductor. We spoke about capacitive reactance, that's the opposition to the flow of an alternating current by a capacitor. And then we spoke about impedance, which is the total, the overall, the effective opposition to the flow of an alternating current that is offered by a combination of resistor and inductor, or a resistor or a capacitor, or a combination of the resistor, the inductor, and the capacitor. And the unit of both reactance and impedance are the same. They are both measured in ohms. So which means that a resistance is measured in ohms, the unit of resistor or resistance is ohms, the unit of reactance is ohms, the unit of impedance is equally ohms. Another area we are going to look at now is resonance. Now, resonance occurs in an AC circuit when the inductive reactance XL is equal to capacitive reactance XC. As a matter of fact, there are 6 things that you need to know about resonance. There are 6 things that are very important that I'm going to consider here. The first thing and most important thing is at resonance, XL is equal to XC. A resonance occurs when the inductive reactance XL is equal to capacitive reactance XC. Not only that, at resonance, the impedance is equal to the resistance. That's another thing that is also very pertinent. At resonance, the impedance Z is equal to the resistance. How does that come about? Let's come here. We still remember this is the formula for calculating our impedance. But don't forget, look at the first condition. Because this is what happens when a circuit is an AC circuit, it's a resonance. The inductive reactance XL is equal to capacitive reactance XC. So if XL is equal to XC, which means here, instead of XL here, I can replace it with XC. Why? After all, XL is equal to XC. And what happens now? We now have XC minus XC. X minus Xc gives us 0. Square of 0 is 0. So which is the only thing under this particular square root now is Z now is equal to square root of R squared. And what is square root of R squared? That is just R. So apart from the fact that we know that at resonance, the inductive reactance XL is equal to capacitive reactance XC, we also know that at resonance, the impedance is equal to the resistance. The third thing that we know is impedance is going to be minimum. Impedance, apart from resonance, if a circuit is not at resonance, impedance is always higher than the resistor. But at resonance, the impedance will not be equal to the resistance because the overall, the net reactance is 0. All right. So here, this is the first equation I gave you. R squared plus XL squared. That's supposed to be impedance. Now, impedance is supposed to be calculated by finding the square of resistance and some other thing, which is XL or XC. But here, impedance now is just equal to R. The lowest value of impedance occurs in an AC circuit when that AC circuit is at resonance. The highest value of current also occurs when this particular circuit is at resonance. So which means that current is maximum. Let's look at the two of them. A resonance circuit will have the impedance minimum. Minimum means it's going to be lowest. It's going to be least. All right. But the current is going to be maximum. Why? They have inverse proportionality. V all over Z. This is the relationship between current and impedance in an AC circuit. You can see that IR is inversely proportional to the Z, which means that the lower the value of Z impedance, the higher the value of the current here. That is why if the Z is minimum, if the impedance is lowest, the current is going to be highest. So at resonance, we have known 4 things now. Number 1, we know impedance is going to be minimum. Number 2, we know impedance is going to be exactly equal to the value of the resistor. Number 3, we know that the inductive reactance XL will be exactly the same as the capacitive reactance. And number 4, we know the current is going to be maximum. Number 5, power factor will be equal to 1. Now, the power factor of an AC circuit at resonance can have various, the power factor of an AC circuit can have various values. But if it has resonance, the value is going to be 1. This is what we refer to as power factor. That's power factor. Power factor is the cause of the phase angle. And the phase angle at resonance, so that I can marry the two of them together, the phase angle at resonance is always equal to 0. So you can see, if you bring out the calculator and find cos 0, what we are going to get is 1. So these are the 6 important things that you are supposed to know about when an AC circuit it has resonance. The phase angle should be equal to 0 degree. And because of that, the power factor, which is having this formula cos of the phase angle, will be equal to 1 or unity as they put it in some questions. The current will be maximum, the impedance will be minimum, the impedance will be equal to the resistance, and most importantly, the inductive reactance is going to be equal to the capacitive reactance. Hope you understand this. Now, another thing we're going to look at is what is the use? What are the applications of resonance? Applications of resonance. Let's just talk about 2 of them. Applications of resonance. What are the practical applications of resonance in an AC circuit? Applications of resonance. Applications of resonance. Number 1, it is used in tuning radios. It is used in tuning radios. It is used in tuning radio. That's one of the applications of resonance. When you are tuning from one station to the other, before you get to that particular station that you want to tune into, you must have begun to actually hear the sound of whatever is being played on that particular station. But immediately, you reach that particular frequency, it resonates, and the sound becomes louder. So when you are tuning your radio, you are making use of an application of resonance in an AC circuit. Another application, or maybe one of us, anyone? Maybe one of you want to tell us one other application of resonance in an AC circuit, apart from using resonance in tuning radio. What else do we use resonance in AC circuit for? Anyone? We've taught this before and we've learned it. So this is not the only application. You want to try? Yes? No, that's different. The resonance when soldiers are marching is different from the resonance in an AC circuit. When soldiers are marching, they are usually ordered to break their march when they are passing over a suspended bridge, so as not to set the bridge into vibration and therefore making the bridge to collapse. That is different from this one. Yes? Anyone? Applications of resonance in an AC circuit. Anyone? Okay, all right, so let's be done. Let's be done. Resonance in AC circuit is also resonance in AC circuit. Resonance in AC circuit is also used in priming, P-R-I-M-I-N-G. Resonance in AC circuit is also used in priming signals. Resonance in AC circuit is also used in priming signals. Priming, P-R-I-M-I-G, in priming signals. The one that is common that JAM often asks is the number 1. Resonance is predominantly mainly used in tuning of radios, tuning from one radio station to the other. And that is because of the variable capacitors in them. I think we spoke about that under capacitor. That's one of the important uses of capacitor in tuning of radio. Just like capacitor is used in tuning radio, resonance in AC circuit is also involved in tuning of radio. And the last aspect of this we're going to be looking at is power dissipated in AC circuit. 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 You should know that power is only dissipated in the resistor alone. Don't forget, in an AC circuit, we can have resistor, inductor, and capacitor. But out of the three of them, power is only dissipated in the resistor. No power is dissipated in the inductor. The same way, no power is dissipated in a capacitor. So in an AC circuit, power is only dissipated in the resistor. And there are two formulae that can be used for that. We can say P is equal to I squared R. And this particular I here is the root mean square value. Because JAMB is notorious for giving you, instead of the root mean square value here, they can give you the peak value of the current. And if you mistakenly use that with the value of the resistor that you are given, the answer will unfortunately be there, even though you are wrong. So ensure that if you are not given the root mean square value of the current, but rather you are given the peak value of the current, ensure that, let's assume that you are given the peak value of the current to be 12 ampere, and you are given the resistor to be, let's say, 10 ohms. Instead of substituting here, and you are now saying P is equal to 12 squared times 10. Rather, it will be this one, first of all, converted to the root mean square value. So which means your IRMS, which is what you need, is going to be the peak value I naught all over root 2. The peak value you are given, that's 12, will be here. Which means the correct way to do that will now be I squared, which is going to be 12, all over square root of 2, everything squared, times the resistor now, which is going to be 10. So ensure that the current you are given is either in RMS. If you are given the current in RMS, you just substitute straight away without any stress. But if you are given the current in peak value, ensure you make use of your formula to calculate the root mean square value of the current. But I can't stress this enough. Power is only dissipated in the resistor. No power is dissipated in the capacitor. No power is dissipated in the inductor. The power dissipated in the capacitor is 0. The power dissipated in the inductor is 0. It's only in resistor that power is dissipated. Another formula that we can use is this. P is equal to V I cos the phase angle. I've already told you that this one is called the power what? The power factor. And this particular angle is the phase angle here. So at times, they can give you the power factor, give you the voltage, and then they give you the current. So easily you can make use of this formula. But most of the time, this is the one that is often used. You can be given the current either in the peak value of the current, which means you still have to convert them to the root mean square value, or you are given the root mean square value of the current straight away. And then you are given the resistor, and you just plug in those parameters into this formula to get the power dissipated. Not only that, other areas that question could come can be, you can come across question asking you that when will maximum power be dissipated in an AC circuit? Maximum power will be dissipated in an AC circuit when the power factor here is maximum. And what's the meaning of maximum? What is the maximum value of cos of any angle? Anyone? 1. That's right. That's the maximum value of cos. Cos of any angle cannot be more than 1. It can be negative, it can be positive, it can be 0, but it cannot be more than 1. If you take out the calculator, for example, and you find, say, cos of 360, do that. What do you have? 1. Try 0. 1 as well. Now try something like, say, 150. So that's the thing. So you can have, at least if you try something like 60, for example, you have positive 0.5. So the cos, the value of this can range from negative to positive. It can be 0 point something, it can be positive 0 point something, it can be negative 0 point something, but it cannot be more than 1. So maximum power will be dissipated in an AC circuit when the phase angle here is equal to 0. And when is the phase angle equal to 0? That's when the current and the voltage are completely out of phase. This current and the voltage here, when they are out of phase, that is when the phase angle will be 0, and that is when the value of the power dissipated will be maximum, because cos of 0 will give you 1, and that is the maximum value of that particular power factor. Let's recap. Power is only dissipated, from what I've told you, in what? In the resistor. No power is dissipated in capacitor. No power is dissipated in an inductor. So the power dissipated in an inductor is 0. The power dissipated in a capacitor is 0. Not only that, maximum power is dissipated when the current I and the voltage are out of phase. So please take note of that. And if you want to calculate your power based on this formula, ensure that the current you are using is the root mean square value of the current. Once again, the current you are using is the RMS value. If you are given the current, if you are given the peak value of the current, ensure that it is converted to the root mean square value by making use of the formula I naught, that's the peak value, divided by square root of 2. So please take note of that. Just in few seconds, let's recap everything we have done. We've discussed about alternating current, saying that it is a current that can change its direction. And we said that alternating current can be converted to a direct current by using a rectifier like a diode. Not only that, we spoke about reactance, which is measured in ohms. And we say reactance is the opposition to the flow of an alternating current provided by either an inductor or a capacitor or both. And we said there are two types of reactance: capacitive reactance, XC, inductive reactance, XL. Not only that, we spoke about impedance, which is the total opposition or the effective opposition or the equivalent. Those are the three words they are using: total, opposition, effective, and equivalent opposition to the flow of an AC current, alternating current, by the combination of a resistor, inductor, capacitor, or both. So which means that it's either resistor and capacitor, resistor and inductor, or combination of resistor, inductor, and capacitor. And once again, impedance is also having a unit with the same as reactance, which is ohms. So unit of reactance, ohms; unit of impedance, ohms; unit of inductor is Henry. And then we spoke about how the current and the voltage, how they are related in a capacitive circuit. In a capacitive circuit, the current leads the voltage by pi over 2 or 90 degrees. In an inductive circuit, I did draw the vectorial diagram for you. The current lags behind the voltage by 90 degrees or pi over 2. And I spoke about resonance in an AC circuit. And I told you that resonance occurs in an AC circuit when the inductive reactance XL is equal to capacitive reactance XC. Not only that, I told you that when a circuit is at resonance, the impedance will be equal to the resistance. Z is equal to R. The impedance is going to be lowest or least or minimum. The current will be maximum or highest. Not only that, the phase angle is going to be 0. Don't forget, phase angle can also be written as angle of lead or lag. You can come across a question asking you that at resonance, the angle of lead or lag in an AC circuit is that. That is another way of asking for the phase angle at resonance, in which case the answer will be 0. And not only that, I told you that the power factor of an AC circuit at resonance is 1 because cos of 0 is going to be 1. And I think the only thing that I did not mention is at resonance, the net reactance, what the meaning of the net? Overall, the total. At resonance, the net reactance is 0. Please take note of that. I didn't include that. That will be number 7. At resonance, the net, N-E-T, the net means total or overall. At resonance, the net or overall reactance is 0. Why is it 0? Don't forget, at resonance, XL will be equal to XC, isn't it? And the two of them will have cancelled themselves out. So at resonance, the net reactance is always equal to 0. So let's take a look at some questions to revise this before we go. Let's look at some questions on AC circuit. Okay, so the first one, the power factor of a pure resistor is dash. A is 1, B is 0, C is 0.5, and D is infinite. What will be the power factor of a pure resistor? It's always 1. Cos of 0 will be 1. Let's look at the second one. Okay, so in an AC circuit, power is maximum when voltage leads the current, B, voltage lags the current, C, voltage and current are in phase, and D, voltage is 0. Which one will it be? Of course, when voltage and current are in phase. Let's take a look at the third one. The power factor of a pure inductor is dash. 1, B, 0.5, and infinite. Is power dissipated in an inductor? If power is not dissipated in an inductor, what will be the power factor of an inductor? Is 0. So let's take a look at number 4. The net reactance at resonance is dash. What will it be? That's the 7th condition, I think, at resonance. So that's that. And then the 5th, and I think the last one, which of the following is true about an AC circuit at resonance? Roman figure 1, impedance is minimum. Roman figure 2, current is maximum. Roman figure 3, net reactance is 0. Roman figure 4, phase angle is 0. Roman figure 5, power factor is 1. Which one will it be? All of them. That's right. Everything there. From Roman figure 1 to 4, all of them are true about an AC circuit at resonance. Impedance is minimum. Impedance is not just minimum, it is equal to the resistance. If you look at Roman figure 2, current is maximum. Why? You can still see here, current is inversely proportional to the impedance. If impedance is minimum, then current is going to be maximum. And then Roman figure 3, the net reactance is 0. I just told you that a few moments ago. And then Roman figure 4, the phase angle is 0 as well. And the phase angle is 0. By the time we plug in 0 into cos, this is the phase angle, cos 0 degree now gives us 1, which means the power factor, which is cos of the phase angle, will be equal to 1. I hope you understand this. Okay, so we're going to switch our attention now to another aspect. This time around, we are going to be looking at friction for some time. Friction, I'm going to be looking at friction, both solid friction and also viscosity. I'm going to be doing the two of them together. Friction. Okay, so You be the decider, I don't know.
nǹkan tó ṣẹlẹ̀ ni pé a máa swap sí chemistry ní 3:30
Can you time on this one?
5 minutes to 3 so possible.
5 minutes or 3? Okay. How many minutes more than this?
Ok bí a ká ẹ mọ̀ ọ́ tó ṣẹlẹ̀ ẹ parí physics ní 3:30 chemistry 3:45
Okay. How many can you time?
ẹni 35 minutes.
35 minutes. Okay, no problem.
Ẹ jẹ́ káwọn ọmọ yẹn mọ̀ that chemistry will stop by àdínkù àdíẹ̀sẹ̀.
Okay.
Hello. Yeah, hope you are staying. All right. So it's because we have already started it. But all things moving forward, I've told him that the physics class will start by 3:30. What is physics starts by 3:30? Chemistry will start by 3:45. So chemistry will now be from 3:45 to 6 p.m. straight. Are you getting it? So by 3:30, you get to just have 15 minutes break. So 3:45 to 6 chemistry. Hope it's clear.
Okay, so we have roughly 30 minutes or thereabout for friction. So let's see how far we can go. So friction. Now we know friction is a force that opposes motion. That's just the basic definition of friction. Friction is defined as a force that opposes motion because when a body being acted upon by friction moves in one direction, friction always moves in the opposite direction to oppose it. And we have different types of friction. We have solid friction, for example, which is the friction between, for example, if we have, let's say, a box, and a box is on this floor, and we are pushing that particular heavy box on the floor, the friction between that particular box and the surface of the floor will be a solid friction. We also have friction in fluid, all right, called viscosity. So maybe we should talk about that first. Now, viscosity is defined as a frictional force that exists between layers of fluid. Once again, viscosity is defined as frictional force that exists between layers of fluids. Viscosity is defined as frictional force that exists between layers of fluids. And if I'm talking about fluids, a lot of people think that fluid only talks about liquid. No, fluid comprises what and what? Liquid and gases as well. So when a fluid, say an engine oil or water, for example, is flowing, the various layers, the layer of the fluid next to another layer, there is always friction in between them. So that particular frictional force that exists between one layer of a fluid and the other layer of that same fluid is called viscosity. And viscosity, just like friction, also opposes motion. It is only occurring in fluid rather than in solid. Now, there are factors that affect the viscosity of fluid. Let's look at the factors affecting viscosity of fluid. Factors affecting viscosity of fluid. There are just about 3 main factors. Factors affecting viscosity of fluid. Number 1 is temperature. Number 1 is temperature. Number 1 is temperature. And here, a lot of confusion, a lot of mistakes are being made. A lot of people believe that, a lot of students believe that when the temperature increases, viscosity decreases. That's not the case for every substance. Now, I told you that fluid is made up of liquid and gas. When the temperature of a liquid increases, viscosity decreases. But in case of a gas, when temperature increases, viscosity of that particular gas also increases. So which means that temperature has different, change in temperature has different effect on liquid on one hand and gas on the other hand. But if you come across question simply asking you that as the temperature of a liquid increases, its viscosity will dash. Now that's a liquid. When you increase temperature of any liquid, the viscosity always decreases. Let's paint a picture. Because what viscosity means, viscosity simply means that the unwillingness, all right, of a fluid to actually flow. Because viscosity actually tends to slow down or reduce the speed with which a fluid flows. Let's take water, for example. Water has very low viscosity. If you have water in a jerry can and you open it and you are pouring it into another container, the water flows very easily because of very low viscosity. But if you have a jerry can also, this time around filled with palm oil, or maybe filled with onion, or filled with, say, glycerin or lubricating oil, engine oil, how easily does it flow when you are trying to pour it? It flows sluggishly now because the viscosity in those things like palm oil, onion, engine oil, glycerin is very, very high. And the higher the viscosity, the more slowly and sluggishly that particular fluid will flow. But guess what? If you put palm oil that doesn't flow easily, you put it on fire, for example, and you eat it, what happens? It melts. And by the time you want to pour it now, what happens? It flows very easily. What has happened? The heat that you have applied to it has actually reduced the viscosity in it. So viscosity will reduce when the temperature of a liquid increases. But viscosity will increase when the temperature of a gas increases. So please take note of that. Increase in temperature will increase the viscosity of gases, while increase in temperature will reduce the viscosity of liquid. That's number one factor that affects viscosity, temperature. Another factor that affects viscosity is pressure, and it's a linear relationship. The higher the pressure, the higher the viscosity. So that's that. Another factor that affects viscosity is pressure. As the pressure increases, viscosity also correspondingly increases. And the third one is nature of the fluid. Nature of the fluid, or we can just say nature of the liquid. Different liquids have different viscosities because of their nature. For example, I use water for you. Water flows easily because it has low viscosity. Engine oil, on the other hand, flows sluggishly because the viscosity is higher than that of water. Onion flows sluggishly because the viscosity is higher than that of water. Glycerin has some of the highest viscosity of different fluid. So there are various categories of fluid that will flow. If you want to pour kerosene, for example, it's very fluid because the viscosity in kerosene is very, very low. The same thing with petrol. But if you want to pour, if you are pouring petrol side by side with that of a diesel, you will see that the diesel is going to pour more sluggishly, slowly, because a diesel has more viscosity than kerosene. So those are the three factors that affect viscosity. Number one, temperature. The higher the temperature of a liquid, the lower the viscosity. The higher the temperature of a gas, the higher the viscosity. Number two is the pressure. The higher the pressure, the higher the viscosity. Number three is the nature of the substance or the nature of the fluid. Different materials, different fluid have different viscosity. That is why water flows easily because of its low viscosity, whereas onion or palm oil flows more sluggishly because they have higher viscosity. So another thing I'm going to be talking about is what is the effect of viscosity around us. Now, viscosity has various applications. Maybe we should look at that. Applications of viscosity. Applications of viscosity. Let's look at areas in which viscosity are applied. Applications of viscosity. Number one is lubrication. If you look at lubricants that are being used, like engine oil, for example, we always use lubricants based on their high viscosity. When you are choosing a fluid to be used as a lubricant, the reason why you are choosing a particular fluid is because such a fluid has high viscosity. So lubricants are chosen due to one reason: their high viscosity. Not only that, viscosity is also applied in the effect of viscosity is felt even in rainfall. Now, if not because of viscosity, all right, that helps the viscous drag that helps to slow down raindrops at its force from the sky during rainfall. If these raindrops are not slowed down by viscosity, the speed with which they will get to the earth's surface and strike you and I will actually be damaging. Take a look at this. Because it's one area that JAMB actually focuses a lot. Let's say we have a spherical ball here, and inside here we have a viscous liquid like glycerin. When you drop this metallic ball into this, don't forget a metallic ball. What happens to it? It begins to move very quickly, begin to sink, begin to move at the high speed while sinking down inside this particular tube. And because it's having a mass, the weight is going to act downward. And there are going to be two upward forces opposing the motion of this. One will be the upthrust, and the other one is going to be the drag, called the viscous drag. But initially, because the weight of this particular spherical metallic ball is higher than the sum of the upthrust U and the viscous drag, that particular metallic ball will be accelerating, moving very, very fast, sinking down. But it's going to get to a particular stage where the weight of this metallic ball, which acts downward, will be counterbalanced. Counterbalance means that it's going to be cancelled out. The weight is going to be equal to the two upward forces, which means that a stage is going to be reached when the downward force mg will now be equal to the sum of the upward forces, upthrust, plus the v, which is viscous drag. At this particular stage, the metallic ball does not accelerate anymore. It now begins to fall steadily. We call that particular stage a stage at which it reaches terminal velocity. And that's what I'm talking about. When rain drops during rain, it initially falls to accelerate, moving with an incredible high speed. But it doesn't just move with that particular high speed or acceleration to the Earth's surface. It's going to get to a particular stage where it attains a terminal velocity, at which point it begins to fall down with a uniform velocity. It's no longer accelerating, so that by the time it lands on our earth, on our faces, and so on and so forth, it has actually slowed down to a level that it poses no effect or damage to us. And this equation is important because there are a lot of JAMB questions that will give you 4 equations and ask you that which of the following equations is true about an object falling through a viscous liquid at terminal velocity. Once again, at terminal velocity, the downward force, which is weight, is going to be equal to the sum of the two upward forces. What are they? The upthrust U and the viscous drag, which is V. So this equation is true at terminal velocity. Please, let's take note of this. At times, you can bring the right hand side of the equation to the left hand side. So it can be written as mg minus u minus v is equal to 0. That is another way the question could come. Instead of the equation to be written as mg is equal to u plus v, at terminal velocity, it could be written as mg minus u minus v is equal to 0. So these are the two equations that satisfies a ball that is falling through a viscous liquid at terminal velocity. Please take note of that. And don't forget, when an object is falling at terminal velocity, it means acceleration is equal to 0. Because terminal velocity is called uniform velocity. And don't forget, when the velocity is uniform, acceleration is 0. Don't forget, acceleration is calculated by subtracting the initial velocity from the final velocity and dividing it by the time. But at terminal velocity, the initial velocity and its final velocity are actually equal. So v minus u will be equal to 0. So at terminal velocity, an object that is falling through any viscous liquid is going to have acceleration being equal to 0. Let's take note of that. Now let's talk briefly about solid friction. Now, we experience friction and the beneficial effect of it every single day. When you walk from one place to the other without actually falling or maybe sliding on a wall and on a floor that is very smooth, that is the effect of friction. When a car is moving on the road and a driver maybe steps on a brake and that particular car is brought to a halt or stop due to the friction between the tire and the surface of the road, that's an application of friction. Not only that, when we are grinding, when people grind, maybe using stone and so on and so forth, that's an application of friction. So friction is applied in a lot of ways for a lot of beneficial uses. However, there are also the various disadvantages of friction. But before we get to that, let's talk about loss of friction. I've defined friction to you earlier by telling you that friction is a force that opposes motion. Let's look at the 5 laws of friction. Laws of friction. The first one is friction opposes motion, which is what I've said earlier. Friction opposes motion. Don't forget, friction does not just opposes motion. Friction will always move in the opposite direction to where the object is moving. So which means if you have a box like this, and this box is being pushed in this direction, the friction will act in the opposite direction. So friction doesn't just oppose motion, it acts in the opposite direction to the direction in which an object is moving. If you are moving in the forward direction, the friction between the sole of your feet and the floor is going to be moving in the opposite direction, which is backward. So number 1 law of friction is friction opposes motion and friction acts in the opposite direction. Number 2, friction is directly proportional to the normal reaction. Friction is directly proportional to the normal reaction. This friction is directly proportional to the normal reaction. Normal reaction is represented by capital letter R. And don't forget, normal reaction is a product of the mass in kilogram and the acceleration due to gravity. It could be in 9.8 meter per second squared or perhaps in 10 meter per second squared. So friction is directly proportional to normal reaction. And if you want to replace the proportionality sign with equality sign, we introduce a constant. So friction now is equal to rho r. So this is the normal reaction. This particular one here is what we refer to as coefficient of friction. There can be 3. We have coefficient of solid or static friction. We have coefficient of static friction. We have coefficient of kinetic friction. We have coefficient of rolling friction. So these can be of 3 types. If a body is stationary on a particular floor, if you have a bag of cement placed on a floor, the frictional force that exists, the coefficient of friction that exists between that bag of cement and the surface of the floor on which it is placed is that of static friction. Because the cement is there, it's not moving at all. And then we have coefficient of kinetic friction. Now, if you are walking from place A, maybe from point A to point B, there's always friction acting between the sole of our feet and the floor on which we are walking. So that kind of kinetic friction, that kind of coefficient of friction is coefficient of kinetic friction that has to do with motion. And then let's assume you have a drum, and then you place the drum on its side, and you are rolling that particular drum on the surface of a floor. The coefficient of friction between that particular drum that is being rolled and the surface of the floor is going to be coefficient of rolling friction. So you can see the difference between the three of them. Coefficient of static friction, that's the frictional force that exists between an object that is stationary on a particular rough surface. Then coefficient of kinetic friction only applies to an object that is in motion, like a person maybe walking or rolling. And the coefficient of rolling friction, maybe like a drum being rolled, or maybe a ball being rolled on the surface of a field or on the surface of a floor, for example. And you must know that coefficient of static friction is higher than the coefficient of kinetic friction. Once again, coefficient of static friction is higher than coefficient of kinetic friction. Not only that, coefficient of kinetic friction is higher than coefficient of rolling friction. The first thing I said was coefficient of static friction is higher than coefficient of kinetic friction, while coefficient of kinetic friction is higher than coefficient of rolling friction. So please take note of that. It is the coefficient of kinetic friction that is highest out of the three of them. So let's go ahead to number 3 now. Don't forget we're talking about the laws of friction. Number 3, friction is independent of the relative speed between a body and the surface. Friction is independent. Independent means it does not depend, it's not affected by. Friction is independent of the relative speed between a body and the surface on which the body is placed. Friction is independent of the relative speed between the body and the surface, which means that if a body, imagine a box that is pushed on this surface, on the surface of this floor like this. If you push it and then it begins to move, if it moves with a velocity of 10 meters per second squared, and you have another box and you push it and it is moving with a velocity of 50 meters per second squared, one is 10 meters per second squared, the other one is 50 meters per second squared, the friction that will be affected by both of them will be the same. Friction does not depend on the speed with which a particular body is traveling on the surface of a rough surface. Number 4 now, friction is independent of the areas of contact between an object and the surface. Friction is independent of the areas of contact between the object and the surface. And lastly, friction depends on the nature of the surfaces. Friction depends on the nature of the surfaces. Now, let's take it from number 3. Number 3 is talking about friction not being affected, being independent of the relative velocity. For example, if you look at this board, if I rub my hand like this, just slowly like this, the friction between my palm and this will be the same with when I'm rubbing my hand by increasing the speed with which I'm rubbing my palm on it. So friction doesn't depend on the speed, on the relative speed between an object like my palm here and the surface of a particular rough place. Not only that, friction does not depend on the area between an object and the surface. If you have a box. You have a box like this, and you can imagine the area, and you have another box that is as big as this with a large area. The friction between this box with a small area and the surface of a rough floor will be the same with the friction between this large box with a larger area and the surface of that same floor. So friction does not depend, it is independent of the areas in contact of an object and the surface. But if you look at number 5, friction actually depends on the nature of the surfaces. That is the major determinant. That is why a smooth surface like this particular board now is smooth. So there's going to be very little friction between my palm and the surface. But if I'm rubbing my palm against the wall, as you can see there, those walls, you don't need to touch them. You can see they are actually coarse in nature. They have rough surfaces. So the friction between my palm and the walls are actually going to be higher because of their rough surface. But the friction between my palm and this particular smooth surface is going to be lower. So friction depends on the nature of surfaces. Is the surface smooth or is the surface rough? Friction is going to be highest on a rough surface and is going to be lower on a smoother surface. As a matter of fact, when you have a perfectly smooth surface, there is not going to be any friction. Friction is zero in a perfectly smooth surface. So friction depends on the nature of the surfaces. So please, let's take note of those 5 laws of friction. The first one was friction opposes motion, and friction always acts in the opposite direction of motion. Number 2 was friction is directly proportional to the normal reaction. Number 3 was friction is independent, that is not affected by the relative speed or velocities of an object and the surface. And number 4 was friction is also independent of the areas of that particular object and the rough surface. And finally, number 5, friction actually depends on the nature of the surfaces. And don't forget, static friction, the coefficient of static friction is always higher than coefficient of kinetic friction. And coefficient of static friction will also be higher than coefficient of rolling friction. So let's please take note of that. Now, let's look at advantages of friction. What are the advantages of friction? I've mentioned some of them. Friction is what enables us to be able to walk without falling. All right? So the ground will have always been most slippery and difficult and impossible for us to walk on were it not to be friction. The friction between the sole of our feet and the floor, that's what enables us to walk easily without falling. Not only that, friction actually enables tires, all right? The friction between the tires of a vehicle and the surface of the road enables a car to come to a stop when brakes are applied. If not, when a car begins to move, it will have been impossible for that particular car to stop. It is friction that enables a car to stop when a driver applies or mashes the brake. Not only that, friction also helps in generating charges. As a matter of fact, one of the ways in electrostatics in physics of generating charges is by contact, isn't it? Now, if a person strikes maybe a stone with a cutlass, what do you generate from it? You generate electric sparks from it. What brings about that? That is through the friction between that particular cutlass and the surface of that particular stone. So, and this and a whole lot of other advantages. So there are a whole lot of advantages that friction affords. But just like everything that has an advantage also tends to have disadvantage. Friction has several disadvantages. Maybe we should mention just 3 of that disadvantages of friction. The number 1 disadvantage of friction is friction always reduces the efficiency of machines. One of the reasons why efficiency of machine is never 100% is because of the influence of friction. because work has to be done to overcome the friction. Because of that, the work output of a machine is always less than the work input. Don't forget, the efficiency of any machine is calculated by the work output divided by the work input multiplied by 1,000. If the work output is equal to work input, efficiency will be 100%. That is why an ideal machine will have efficiency of 100%. What is an ideal machine? An ideal machine is a machine in which there are no friction. When frictional force does not exist, when every part of that particular machine is perfectly smooth. Because a smooth surface means there's no friction, and there's no ideal machine anywhere, because efficiency of machine is always less than 100%. Why? Due to the disadvantage of friction. Not only that, friction always produces heat. All right, friction. That's why if a machine is working, after some time it becomes hot. Why does it become hot? Because of the frictional force between the various parts of it that are moving against each other. So another disadvantage of friction, apart from the fact that friction reduces the efficiency of machine, friction brings about production of heat. It makes excessive heating to be possible in machines. That is why when machines is working for say 5, 10, 30 minutes, you begin to see that the machine is becoming hot because of friction. Not only that, friction causes wear and tear. If not because of friction between the surface of the road and the tires, when the driver buys a tire to the car, those tires could be used for several years. But because when the driver mashes the brake and brings the car to a stop anytime, every time that happens, the friction between the tire and the surface of the road is going to gradually begin to make that particular tire to become more smoother and smoother. All right, the treading of that particular tire will be going until you can actually see the wires that are inside that particular tire coming out, and then the tire will have to be periodically replaced by the driver. So friction also brings about wear and tear. And the same thing happens if a person maybe has a cloth. I mean, imagine children, for example. Imagine children maybe who go to amusement parks and then they are on carousels, for example, they slide down carousels. If they do that severally, you will notice that the very back of maybe their trousers that they are wearing will now become thinner because of the friction between, when they are sliding down, the friction between that particular cloth and the surface of the carousel as it is moving around. So friction reduces efficiency of machine. Friction leads to generation of heat. And not only that, friction brings about wear and tear in substances. Now, how do we reduce friction? Let's run the class up with that. Ways of reducing friction. What are the methods of reducing friction to prevent these disadvantages that I've enumerated? Ways of reducing friction. Number one, by lubrication. When we lubricate the various parts of an engine, we are helping to reduce, to minimize the friction that exists between those moving engine parts. So friction can be reduced, can be minimized by lubricating the engine or a particular surface. And as a matter of fact, even though water is not a lubricant, fluid generally tend to help to reduce solid friction. Let me give an example. If you live in a tiled house, if there is no water spilled on the floor, you can walk around easily without any fear of falling down. But what happens if water is spilled on the floor and it's not mopped? Now there is high incidence of a person walking there and then the person slid and the person falls. Why? That particular water on that particular floor will have reduced the friction between the surface of that particular floor and the sole of the feet of people in that particular house. The same thing, if rain falls, it is more harder to bring a car to a stop when a driver mashes the brake compared to when rain had not fallen. Because when rain has fallen, the moisture on the surface of the tarred road actually help to reduce friction between the surface of the road and the tires of the vehicle. So lubrication helps to reduce friction. Not only that, use of ball bearing. Use of ball bearing. That is another way of reducing friction. Use of ball bearings. Ball bearings are spherical balls, metallic balls that are used in various engine parts to reduce friction between various parts of that particular engine. So use of ball bearing. Number 3 is streamlining. Number 3, streamlining. S-T-R-E-A-M-L-I-N-G. Streamlining. Now, what do you call streamlining? Streamlining is when objects are designed in such a way that they limit the resistance, either it is solid friction or it is maybe viscosity. Now, for example, if you look at aircraft, you look at an airplane, for example, you will notice that the tip of it is actually pointed so that when it flies in the sky, it helps to reduce and minimize the viscosity, the air friction that it encounters in the sky. Not only that, if you look at fish in the ocean that swim around water, if you look at their head, they are never flat, they are pointed, that's streamlining, so as to ensure that as they are swimming in water, there is very low amount of friction or opposition as they swim along. So we've spoken about 3 methods of reducing friction. Now we've spoken about lubricating by applying a lubricant. Lubricants are those liquids of high viscosity that are applied to machine parts to reduce or minimize friction. Number 2 is by using ball bearing. Number 3 is by streamlining. When objects are streamlined, it helps to reduce both solid and viscosity, which is friction in fluid, either in air or in water. So these are some of the ways of reducing friction. We're not done with friction. Come back to the calculation aspect perhaps in our next class. If you have questions, I can take them before we go for the short break. Any question? Any question? All right, so we are done. Then you go for your break and then we come back for. Any question? So let's go for a break.